So I am continuing on with this linear algebra series as part of my project, and today I'm going to be talking about kernel, not so much about the definitions, but more on the look of why and how kernel differs from the null space. I was first introduced to null space in my earlier linear algebra classes, but I didn't really know how it differed from kernel, which was brought up later, until after many practices and just to see it. I thought I'd simplify the process and show people how it differs, and be the person that points it out. So they go over these little details and they assume you would figure it out, but sometimes you figure them out after it matters. Anyways, so yes, talking about the kernel. I'm gonna start with the definition. Kernel of T, or you can write it as ker T, is a subset of V consisting of all the vector V's in space V, such that the T of the vector V maps it to 0. And I just want to point out that this 0 lives in W if we are looking at some T from V to W. So that's the W that the 0 lives. This 0 lives in this W, and this vector V is coming from this space. Just to save some time, I'm gonna just state that. State that the kernel is a subspace. You can try and prove that for yourselves, but I don't want to waste time doing that right now. And just to give you another way of looking at it, the mathematical way of looking at the definition, the kernel of T can be written as this, the definition. Some vector V in V, and you have such that this happens. And remember, this 0 lives in W, and this V lives in V. It's really important to know where things are coming from in this case. So let me just write this out. And when we're talking about kernel, the kernel of T, the kernel always lives in this space W, and this space V. So you can find the kernel of T. It's a space, so subspace of V. Not that I'm looking at it right in this video, but I'd like to point out that W, you can find the image space of T. I think it's really important to know and have this definition set if you really want to understand what a kernel is, because this is where this is how you separate the null space from the kernel, at least from my understanding. So let me show you through an example. So we're going to let T be a linear map, and T from a 2x2 matrix to another 2x2 matrix, and T is defined by, you plug in a matrix, and what you get is a matrix, and the matrix is transpose, subtract the matrix itself. And in this case, they gave us an basis vector. So alpha and beta happen to be the same, which makes a question really easier to handle. And they are here. I'm going to name them because they're kind of, I don't want to keep rewriting them. So just remember, I'm writing this as V1. This is going to be V2. This is V3, and this is V4. And the question asks us to compute kernel of T. And in order to do this, we first need to get, let's stick with purple. We first need to find the matrix. This matrix right here. So basically what this means is I'm going to be finding the transformation of T with respect to basis vectors in alpha. So what were they like? You're going to be plugging in each of the VI's, where I is some 1 to 4. Each of the VI's plug them in here, and you will get an answer, some answer star, and you have to write this answer star in terms of the basis vector beta. In this case, they happen to be the same, so that really does simplify things. And we're just going to start. So V1 is this. We're going to write that out. And it's going to be its transpose, which is itself, because, you know, the transpose, let me just write this out. So when you have like A, B, C, D, and you want to find the transpose of that, well, A and D stay the same place, but you end up switching B. It's like going across the middle or diagonal, and you flip what's on this side and one on that side. That's too messy. Erase that. Let's go back to purple for examples. So it's going to be this minus itself because it doesn't flip, and you get this. And we have to write this in terms of beta. Well, beta does not have any what was like V1, V2, V3, and V4. You can get this by making each of them V1 plus 0 V2 plus 0 V3 plus 0 V4. It's important to know. Notice that's the only combination that you can have with each of the VI's in order to get this 0. Okay. Let's try the next one. 0, 1, 0, 0. Saving us time. I'm going to skip it. Skip the actual step and just show you what this is. And I can rewrite this in terms of the VI's as minus 1 V2 plus V3. 1 V3. And again, notice these. You need to know what's in front. So I'm going to go to the next one, 0. And that one is going to be 0. And that in terms of beta, it's going to be 1 V2 plus minus 1 V3. And I'm going to circle these because these are going to become T's that we need. The columns of T. And the last one, 0, 0, 0, 1. Well, it's going to be 0, 0, 0, 0. And again, it's going to be 0 V1 plus 0 up to 0 V4. And that's it. Well, remember, in the first one, we got a complete row of zeros of 0. It's 0 coefficients, so that comes down here, 0 V1, 0 V2, 0 V3, 0 V4. In the second one, we had 0 V1 and minus 1 V2, 1 V3, and then 0 V4. The third one is like as follows. And the fourth one right here that you can see are all these zeros. So now that we have that, we can go on to calculate or compute for the kernel. And to compute for the kernel, you have to compute for the null space first. Null space. So in null space, the way you would do it is that you would, let me just 0, 0, minus 1, 1, 0, 0, 1, minus 1, 0, 0, 0, 0, 0. You would compute and find it for the 0 right here, right? And you would row reduce it. Row reduce. I'm going to save us some time. I'm assuming that you can do row reduction. So you can get this. You'll get this if you row reduce it. Minus 1, 0, 0, 0. I mean, yeah, it's just one step really for this row reduction. And the null, actually let me take a step back right here. I'm gonna let this be x1, x2, x3, x4. Anything that doesn't have a leading one, I will give it some letter. So for example, x1 will be R. x2, I'll come back because it has a leading one. x3, I'll let it be S. And x4, I'll let it be T. x2 can be written in terms of x3 and so it will be, x2 will be minus S equals to 0, which is basically saying x2 is S. And if I want to write that in terms of null space equals to the span. I'm not going to have space for this edge. Trying to shrink things, and the library is closing, so I'm trying to do this quickly enough to pass on the information. Will be okay, let me just take a step back right here. So you can see that we have some R 1 0 0 0 plus S 0 1 1 0 and T 0 0 0 1. We can say that the null space null of T is the span. It's important to write the span, don't forget it. Is going to be 1 0 0 0 0 1 1 0 0 0 0 1. But that is not the kernel. Remember, the kernel lived in here, and it was it lived in W and in V, and V is a 2 by 2 matrix. So it was in the format that we have it for. Let me just copy this and put it over here. So this set over here would not be the kernel because it's written as if it was in Rn, and ours is in 2 by 2 R. So we have to rewrite this in terms of the space and 2 by 2 R, which I think I forgot to mention this, but alpha, the basis vector is alpha. Alpha is a basis vector telling you for each space. So alpha, basis vector for V, and this one's for beta is for W. So we need to write it in terms of basis vector alpha, which was V1 to V4. I don't want to rewrite the full matrix. I mean, it wouldn't hurt. It wouldn't hurt. Yeah, I'm just gonna do it. So 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So we gotta write this out in terms of that. I'm gonna take this 1 0 0 0 and write it out. So it's gonna be 1 1 0 0 0 here plus 0 plus 0 3 plus 0 4. It just equals back to 1 0 0 0. And you do the same with the next one. What was the next one? 0 1 1 0 0 1 1 0. It's gonna be 0 V1 plus 1 V2, which was 0 1 0 0. Plus 1 V3, 0 0 1 0 plus 0 V4. And that gives you 0 1 1 0. And similarly for the last one, 0 0 0 1, you can rewrite that out and it'll give you 0 0 0 1. So kernel of t is the span. Don't forget to write span. It's one of the things many people would forget. And I'm going to input this, and this. 1 0 0 0 0 1 1 0 0 0 0 1. And we are done. I just want to stop right here and show you or point out something that I noticed.